Okay, so a little bit of a review. We are doing lots of trig functions over the next couple of weeks. A lot more identities than we've been using. So give us a little bit of a review of trigonometry. While you're doing this, have a somewhat philosophical question. And you can answer this with your neighbor, discuss this with your neighbor. Should we teach students like you how to do things by hand that a computer or calculator can do? So go ahead and discuss. You can explain why or why not. Okay, take 20 more seconds. All right. Okay, so we'll do a snap quiz. We're going to start off with yeses, meaning yes, we should teach you how to do things by hand that the calculator can do. And then I'll ask for no. So if you agree with yes, go ahead and snap. If you agree with no, go ahead and snap. Okay, not as many no's. Okay, so someone give me some arguments. Let's just pick like 4. Okay, yes. Okay, great. So right here in the green shirt.
Oh, sometimes I can't be bothered to get out like technology or anything like that. So if I'm low on supplies, being able to do stuff by hand is really helpful.
Okay. I mean, yeah, there's like 2 times 3. You're not going to take the time to pull out your phone and type in 2 times 3, right? Even though your calculator can do that. Like there's some things that are so basic you shouldn't need to.
Are we assuming that's the equation?
All right, so his comment was, what are the equations going to be like? Are we talking about simple things or are we talking about complex things? Right, because for the simple ones, you might be like, hey, maybe we should know how to do the simple ones by hand. The complex ones, maybe it's not worth the time if we already can do it.
I mean, you might need to know the simple ones to use a computer instead of the complex ones.
Okay, so you might need to know the simple, so you can use a computer to do the more complex ones. Okay, last one right here.
Yeah, if you could make this argument the same way you talked about trying to teach information from your science. Like when you're writing a program, you don't need to know all the fundamental basics. But you need to know numbers before so you can flow into solving your writing program. Same way I think that applies. Maybe you don't necessarily need to know all the math stuff, but you need to know so you can implement it to.
Okay. All right, so well, especially these last 2 comments bring up the real question, which we should be asking, which is, what should we teach that a computer and calculator can do, and what shouldn't we teach that a computer and calculator can do? I'll give you my, well, why am I bringing this up now? Because the next several sections, what we're teaching you are things that you can just type into Wolfram Alpha. We're teaching you integration techniques on how to find things by hand. And some of them you might think are kind of pretty basic, allow you to do some pretty basic things. Some get pretty technical, and you might think, why am I learning how to do this? There are sections coming up the partial fraction decomposition, if I was going to kick one thing out of the Math 113 curriculum, that would be the one to go. Let me explain why with another example. Where's my pen? Here. Okay, here's a very simple, overly simplified model of real-world problem solving. You have a real-world problem. You turn it into a mathematical problem. This is often called mathematizing. Mathematizing. There are other words for it. That's my favorite one. I don't know if I spelled that right, but. And then you have a math problem. You use your mathematical techniques to find a math solution. You can think of that as calculating or mathematical problem solving or just solving. Okay? And then you take your math solution, interpret it as a real-world solution. That's interpretation. And finally, once you get a real-world solution, that often gives rise to more real-world problems. So where we spend the bulk of time in school mathematics is right here. Right? We give you math problems. You learn how to find math solutions. It's also the one place in this cycle where technology can help you out. So, right, that's really the only place in here where you could use computers and calculators is that arrow, that calculating and solving. Okay. My answer to what should we teach that computers and calculators can do. Well, there are things in this over here doing this arrow that are really helpful to know for these other arrows. And if that's the case, then let's teach it. Because otherwise you're limited in doing the whole cycle. But there are things here there are some things here that really don't help you in other places. For example, we used to teach people by hand how to find square roots. You wanted to find the square root of 745, then there's an algorithm. It looks a lot like the long division algorithm, and it's a little bit more complicated, but you can start working it out, and a lot like long division, you can keep going and go as many decimal places as you need for your answer, right? For your however close you want to approximate the answer. We don't do that anymore, but no one really complains, and I don't think people are out much because we don't teach that anymore. But that's something where it doesn't help you at all in any of these other areas, right? Knowing that algorithm doesn't really give you much, okay? But there are things over here that do give you, they give you tools to work with while you're setting up the problem and thinking about the problem and interpreting the problem and other things. So that's my shorthand idea for what we should teach and what we shouldn't teach. Some of the things we're going to teach, they fit into that category. All, I don't think so. We probably emphasize this stuff a little too much now with things like Wolfram Alpha and Math Picks. Any of you have a Math Picks app on your phone? Oh, one. So Math Picks is really nice. You just write down the problem you want to solve and take a picture of it, and it tells you what the answer is. It's all like photomath, but photomath is only good to like basic algebra. This will do some pretty serious calculus and differential equation stuff. So it's really nice. So yeah, so everyone's now on their phone like Math Picks. So yeah, it's really nice. With stuff like that, we probably do a little too much by hand, but with stuff like that, it doesn't mean that you shouldn't know. You shouldn't know the basics of what's going on, and with a lot of these techniques. So that's 2 bits. All right, let's get back to this. Theta 1 and theta 2. Okay, what did you guys get for theta 1? Okay, I heard an 80 point something and a 100 point something. Okay, what about theta 2? 49 point something. And anything else for theta 2? 69 point something. Should we just take a vote on which one's right here? I'm like, all right, well, yeah. So if you set up an equation, using law of sines, and you solve for theta 1, what do you get? You should only get one solution. What that is. What did you? People that set it up using law of sines, what did you get for theta 1? You got the 80-ish, rounded to 81. Okay, so that's this one that we got. Okay, if you set up for law of sines and you get for theta 2 and you solve the equation, you get an expression. You punch in your calculator. What do you get? Which one of these? The 49 or the 69? I heard both ways. So 49, 69, 49, 69. You should get the 49 one. Yeah? Should. But I hear some grumbling. What's going on? It doesn't add up to 180. You have 30 degrees, 80 degrees, 49-ish degrees, which is basically 50 degrees. You add them up, you get about 160 degrees. We rounded, but that 20 degrees isn't round-off error. Okay? Someone said they think the measurements are off. The measurements are not off. Like, if you can actually make a triangle with those side lengths. That angle is really, really close to 30 degrees, and it is a real triangle. So what's going on?
Are you saying with the lights here?
I'm saying you guys are magic. You guys finally did something that mathematicians haven't been able to do for the history of the world. You found a Euclidean triangle that has less than 180 degree angle. So that's really cool. Alex? Sorry, say it louder. Right, well, yeah, we could take this one and then replace that with the 50 and you'd get your 180 degrees. Or you could take the 100 and replace the 80. So could we just do either one? Okay, here. That shouldn't matter. So no, that's allowed. That's allowed. In fact, that's where this comes from. Okay, so let me explain what's going on here. The conversation we just had about knowing what your calculators and computers can do. You've got to understand what the calculator is doing here when you punch in inverse sine of something. Okay. Sine looks like this, ish. Right? If you give me an angle, I can tell you what the sine is of that angle. The angles are inputs. Okay? But if you give me a ratio, if you give me a sine ratio and say, what angle does that come from? That's what the inverse sine is answering, right? You gave it a ratio and said, what angle does this come from? There's a whole bunch of questions. There's a whole bunch of possibilities with that one, right? Any of those things along there. Is it this angle, or is it this angle, or is it this angle, or is it this angle? Like, which angle is that coming from? Well, your calculator is programmed to only think of angles between a negative 90 degrees and 90 degrees. So no matter what what's the sine ratio you plug in there, you're only going to get angles between those two. And But triangles can actually have angles that are larger than 90 degrees, right? So what you've done, this is 90, and you plugged in a ratio here, and it said, hey, it's 80 degrees. But you have to be smart enough to think, it might not be 80 degrees. This gave me 10 degrees less than 90. It actually might be this one that's 10 degrees more than 90. Okay? So you can't just always trust your calculator. How come it hasn't? The reason I bumped into this is because this did come up in a math class, and the math teacher was like, I can't understand what's going on here. We keep getting the wrong answer. So it does come up. Well, you mean that, well, I should say what is the what you're talking about. That your calculator, that you have to think about what your calculator says? Or, oh, that arc sine is only defined as negative? Because you had poor math teachers. Okay, so become a good math teacher. You know, major in math ed and solve this problem. Yes, Garrett.
So how do we know which one to pick? Whether is it 100 or is it 60?
Okay, so it's going to be 100 because this one has the one that's the potential of being obtuse because the largest angle is across from the largest side. So you know it can't be this one that's going to be obtuse. So this 80 is actually not 80. It's 10 more. It's 10 more than 90, not 10 less than 90. So it's about 149 and 30. About 150 and 30, which gets you your 180. Okay, so let's talk about what we're actually here to learn about, which is something your calculator can do. Okay, so we're doing, forgot what it's called, parts. Okay, we're going to start with parts by looking at, we're going to go back to last semester and do the chain rule for derivatives. So we're going to quickly talk about where this comes from. Oh, that was bad. My U's and my V's look the same. So if I take the derivative of a product, then I take the derivative of the first times the second plus the first times the derivative of the second. Right? Yeah? Yeah, what did I say? Chain rule? Oh, yes. Product rule. Thanks. I think I said chain rule in my last class, too. So how about is that? So we've got the product rule. I'm going to find the antiderivative of all these. This one I can do because the antiderivative of the derivative is just the function. So uv. These doesn't help me a lot here unless I know what the function is. But I'm going to solve for one of these antiderivatives. Okay? And so I'm going to solve for this one. So I'm going to write the derivative of u v prime equals uv minus u prime v. Okay, if I took this one over to this side, it would become negative. Right, so that's where I get the negative from. And what we've done here is we have found a formula that we might be able to use to get a simpler integrand to find an antiderivative of if we have an integrand that looks maybe like a product and we can